Okay, awesome. Welcome to everybody who is joining us via Zoom to our Deep Talks, How Low Can You Go? I am underground, I'm on the 4850 level, and we are getting ready to link this webinar to our Facebook Live. So if you just hold on a second, we'll wait until I get the go ahead to go to Facebook Live. Seeing some numbers filter in now. All right. Awesome. And like I said, I am nearly a mile underground. We are in the Davis campus right now, right outside the Black Hills State University underground campus, which you'll be getting a live tour of later with Dr. Brianna Mount. I'm just gonna hold on a minute until we can link to our Facebook Live. We've got Dr. Brianna Mount and Matthew Capist just through these doors. They're in the BHUC, the Black Hills State University underground campus, getting everything set up for us. Right. Matt's going to give me the go ahead in just a few seconds.
Okay, Aaron, we're live on Facebook.
All right, awesome. We're live on Zoom and Facebook, so we're going to go ahead and get started. For those of you just joining, I am on the 4850 level of Sanford Underground Research Facility. That's nearly a mile underground. We're in the Davis campus, and I am Erin Broberg. I am your host and a communications specialist here at Sanford Lab. So before we get started, I want to go ahead and thank our awesome Deep Talk sponsors. We have Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Chuck and Jolene Lichtenwallner. We want to thank you guys so much for giving generously to support education and science in this region and state. So Crow Peak Brewing Company is sponsoring tonight's door prizes. So I'm going to have Matt go ahead and bring up that poll. We have 3 door prizes tonight. One is a growler with 1 fill. Another is a 6-pack of Crow Peak's locally brewed craft beer. And another is a gift certificate with a Crow Peak t-shirt. So to enter to win this prize, you need to be at least 21 years of age or older, and you must be able to pick up your door prize at Crow Peak Brewing Company in Spearfish, South Dakota. So while that poll is up, go ahead and enter yourself to win. There's some really great prizes. And this is only for those who are viewing via Zoom. So if you're in the Zoom webinar, go ahead and enter yourself. And we will randomly select a winner at the end of the event. So I'm going to leave that open for another 5 seconds. Enter yourself if you haven't yet. And we can go ahead and close that poll. Thanks for doing that, and thanks again to our awesome sponsors. So as you know, we are about to join Dr. Brianna Mount for a presentation and tour of the Black Hills State University underground campus. You might also hear the voice of Sanford Lab's Creative Services Supervisor and tonight's cameraman, Matthew Capist. This setup is a little different from our normal virtual events, so if there's any technical issues, please hang in there, bear with us as we solve issues as quickly as possible. But we would love to hear your questions tonight. So if you're joining us through Zoom, please enter all of your questions through the Q&A function. And if you're watching on Facebook Live, just go ahead and pop those in the chat. To get started, I'm going to introduce tonight's speaker, Dr. Brianna Mount. Dr. Mount is an assistant professor of physics at Black Hills State University, and she's also the director of the BHUC at Sanford Lab. Closely tied to her underground research, Dr. Mount is the director of several outreach activities. She is the organizer and PI of the BHSU Underground Science REU program, the chair of the NSF REU Physics Leadership Group, the organizer of the BHSU Gemadark Summer Program, and the director of the annual BHSU Underground Robotics Competition at Sanford Lab for middle school students. She is also the current chair-elect of the National Organizing Committee for the Conference for Underground Women in Physics, or QWIP. So she's very, involved with outreach, and we're proud to support that here at Sanford Lab. All right, well, now you know Dr. Brianna Mount, so we're gonna go ahead and meet her in the underground campus.
All right, hello everybody. I'll just give Erin a minute to get the slides up. It's so great to see everybody. It's kind of a weird thing today, but we'll do our best. Welcome to the BHSU Underground Campus. And I thought maybe I'd give you an idea of where we are. So Erin, if you can go to the next slide. So I think a lot of you are probably tuning in from Lee. So there's the open cut there you can see on your screen, and you see the red circle. I am basically a mile underground of that red circle. And Erin, if you go to the next one. So this is a diagram of the 48-50-foot level of the Sanford Lab. And so you can see the Yates shaft is in yellow, and also the other shaft is also yellow, the Ross shaft. The BHSU Underground Campus, or we call it BUC for short, used to be at the Ross campus, but over the past year, we've been moving it here to the Davis campus to make way for the new exciting dune experiment with those big green patterns that you can see on the slide there. So it's taken us quite a while. We're still moving, so pardon our dust, but I think it'll be kind of an interesting time for you to see some of the detectors before they're actually built. So hopefully it's a good time. Go ahead, next slide. So the Davis campus has two main experiments. One is the LZ dark matter experiment, and the other is the Majorana demonstrator. And if you want more information about these experiments, there are also other deep talks for you as well. The other really cool thing that I think that's online is you can go on a virtual tour of the entire Davis campus as well. And so make sure you check those out at CERC's website. But otherwise, these two experiments are right next door, literally right next door for Majorana. And what we do here at the BUC is really to help out those experiments and other underground experiments. And go ahead, Erin, next slide. Okay, so before I get to what we do here, I thought I'd talk about a little bit of nuclear physics. So I think people have this kind of weird idea in their head about what a nuclear physicist is. And so I'm going to induct everybody into being a nuclear physicist. And really all a nuclear physicist is someone who studies processes in the nucleus. And so in particular, we talk a lot about radiation. So some people have different ideas of what radiation is. So some people think radiation is a little scary. I'm actually finding in the last little bit, 5 or 10 years, that a lot of students that I ask about radiation aren't so much like scared of it. They don't think of like Chernobyl all of a sudden when they think of radiation. They think more positive things, especially about radiation therapy for cancer. So I think different people have different ideas of what radiation is. I thought I would go really quick through what radiation is. So we'll do the basics of nuclear physics. What I'm talking about right now is ionizing radiation. So people kind of throw around radiation, the word radiation. And so for example, the light that's shining on me is radiation. It's electromagnetic radiation, but I'm going to be talking about radiation in the sense of ionizing radiation. And ionizing radiation has its origins in the nucleus, hence the nuclear physics. Next slide. Okay, so to understand radiation, I'm going to have to bring us back a little bit to high school. I know people have different ideas of how well that went in high school in your chemistry class, but I'm sure you saw something like this up on a wall somewhere in a chemistry classroom in high school. And this is the periodic table of elements. And so everything that's around us, most of all the ordinary matter that's around us, is basically made up of things in this periodic table of elements. And so I think people are pretty familiar with, you see that one there, that's hydrogen, the He, that's helium. We see the carbon with the 6. And so those are basically all of the elements in our world. And they're organized nicely into this table. Now, a couple of things that you have to know that are helpful with this table, and I've got some cotton balls here to help us remember a little bit. So those numbers on top of those different elements are the number of protons in a nucleus. So I'll make those white. Sorry about the cotton balls, they're kind of spotted. I tried to dye them and it didn't go very well. So let's say that white cotton balls are protons. And so let's look at carbon. So carbon has 6 protons in its nucleus. That number 6, that really tells you what the element is. So if you see something with a nucleus that has 6 protons in it, that is always going to be carbon. If you see something with a nucleus of 8 protons, that's always going to be oxygen. The things that change in a nucleus, but that don't change the element, are neutrons. So I thought I'd make these neutrons pink. So in this case, I've got 6 protons, 6 neutrons, and maybe I'll mix them up a little bit. And so here I've got my carbon-12 nucleus. And you can add another neutron. Oops, were these protons? I can't remember. You can add another neutron and make it the same nucleus. If we were to add another neutron to this nucleus, that would be carbon-13. And that's the idea of the nucleus. Now, when you have radiation, you have different things happening in the nucleus. One of the things is beta decay. And so beta decay is when a neutron becomes a proton and emits an electron and a neutrino. And so Aaron, if you'll go back to my slides, can show a little bit more about those processes. Okay, so this ionizing radiation, particles and energies are released due to an unstable nucleus. So really, if this thing is just kind of unstable, it wants to emit a particle. Of about the 3,000 isotopes, remember we have those elements that were in the table, isotopes are just adding neutrons. Of the 3,000 isotopes of the known elements, only about 260 or so are stable. And so most isotopes are radioactive. When a nucleus is not stable, it will emit radiation and transform to a new nucleus that is closer to being stable. Next slide. Okay, so I'm just going to talk about 3 different types of radiation. There's more different types, but these are kind of the, I don't know, the fun ones, I guess you could say. And the way that they came up with their names, I think is kind of interesting. So back when they were discovering these processes, they didn't know what these different particles were. And so they just called them alpha, beta, gamma, because physicists like Greek symbols. I don't know why they call them. I don't know why they didn't do ABC, but they did alpha, beta, gamma. And it turns out that alpha is a helium nucleus. So it is 2 protons and 2 neutrons. A beta is just a fast electron. And I already talked about beta decay a little bit when a neutron becomes a proton. And I don't know which fuzzy ones you like the best, but that's a beta decay. Now, sometimes when you have something like a beta decay and you go from one isotope to another, it is still energetic. And so it needs to release something. And the thing that it releases is a gamma, which is basically a packet of energy. It's a high energy packet. Okay, next slide. Okay, so of course the thing that people think about with radiation is what is it going to do to me, right? And it depends on what kind of radiation you're talking about. So alphas will do damage if they get inside you, but not when they're outside of you, because they get stopped by most things. And you can see this diagram here. Beta, those were those fast electrons. They'll get through some things. They'll get through a sheet of paper and that sort of thing. But you can see they'll get stopped with some plastic or your hand. Gammas, and gammas are kind of what I'm going to talk about today, go through more. And generally it takes lead to stop a gamma. And I've actually got a lead brick here to show this. And I brought in some Fiestaware. And this Fiestaware, I think, has uranium in its glaze. And so this counter will make it click each time it detects a radiation particle. So let's see if we can hear this. You hear that? Okay, so a person maybe will do a couple clicks, a minute or so. I'm not clicking right now. there's one. Is Matt clicking? Matt's not clicking. But anyway, so you can see that there's radiation coming from the plate and hitting my counter. Now, if I put the lead brick in between, it really attenuates those gammas. And that'll come into play in a minute when we talk about what we do in this lab. Okay, go ahead, next slide. Okay, so we just talked about radiation, and I kind of got that out of the way. So what does that actually have to do with what we're doing in this buck right now? And it turns out that detectors like LZ and Majorana are really good radiation detectors. In fact, this is the reason that we're underground to begin with. So when they look for the rare dark matter events or different processes with the neutrino, those happen really rarely. But there's a lot of radiation from cosmic rays on the surface. And so those detectors detect those cosmic rays, and that signal would completely overwhelm the little tiny, not often process, the rare process that they're looking for. And so they go a mile underground, so we've got a mile of shielding to help us out. But then if you kind of look around, and you remember with this Geiger counter, it counted me, right? So I'm radioactive, you're radioactive, the walls are radioactive, everything is radioactive. And so what we have to do with these experiments is find materials that are ultra, ultra pure. So they have really low amounts of radioactive elements in them. And the elements that I'm talking about mainly are potassium, uranium, and thorium. So we're looking for ultra, ultra low levels of radioactive elements in the materials that we're looking for. Go ahead, next slide. So what we do in this facility is we have several low background counters. And what the heck is a low background counter? So we have these detectors that will detect radiation, but they're really, really sensitive. And so this is why we have our buck. Go ahead, next slide. So these counters, this counter is just kind of detecting a radiation particle, right? It's not giving me much information about it. What these detectors here, here's one, this one's called Mordred. These detectors will count the radiation from different materials, and it will tell us what material, the spectra from those counting time will tell us what materials we have and how much we have of them. And what we do is we stick a material, say like a plastic, in these detectors. We go away for 2 weeks and we wait for our counters to count the gammas that are coming off of these materials. And go ahead, next slide. And what we see is something like this. So there's too much on this slide. Just maybe look at one of the spectra here. So let's look at the blue. So this is an example of what we'd see. And we count the gammas, and our detectors also tell us their energies. And that's really important because that tells us which isotope to tie with that gamma. So each one of these peaks that you can see here is tied to a different isotope decay. And we can tie that back to uranium, thorium, or potassium. And so how big those peaks are tells us how much of a particular material we have. And this is important for two different reasons for the experiments. The first reason is if you're at the beginning of your experiment and you go to two manufacturers and they say, we have the best plastic ever, you should buy our plastic. And we say, okay, but then we go to this other guy and he says, we have the best plastic ever, you should buy our plastic. How do you know which one to buy? How do you know which one will have the lower amounts of uranium and thorium and potassium? Well, we can have them compete, right? So we can put one in Maeve, one in Morgan, and wait 2 weeks, get our spectra, and see which one has more radioactive elements. So choosing materials is one reason. The second reason is there's so much cool stuff that goes on with the data analysis of these big experiments. One of the things is they basically build a virtual detector, and you can put in their simulation, okay, this little screw has this much uranium, this light detector has this much thorium, and then you can let the simulation run and you can see what your background will be like for your actual detector. And of course, this is important because we're looking for really rare things. And so you can see what your background will be so that you can know if you have
perhaps seeing dark matter or not. So that's really what we're doing in this lab. Is these are really good radiation detectors, and we're screening materials for the bigger experiments like LZ and Majorana. Go ahead, the next slide. Okay, the Buck is a user facility, and so these detectors are all owned by different people, different entities, I guess I should say. The first that I'll talk about is the most detectors that we have in the Buck, and those are the Berkeley detectors. And so the Berkeley Low Background Counting Facility has this really cool story. It was started by Al Smith over 60 years ago. So they have been doing this a long time. And it's currently directed by Kevin Lesko. This is a picture of Al Smith loading a counter at Berkeley, I think. And these detectors, once they got surf up and going, these detectors moved underground to reduce the backgrounds from the Oroville Dam, actually, where they were in California before. So we've got here Mordred, Maeve, Morgan, and what we call the twins. And we'll do kind of a walking tour in a minute and show you guys those detectors. Next slide. Okay, so then we have 2 other counting systems too. One is not built yet, but it'll be right here. And so this is the table. You can see the Germanium-4 counter. That's the counter as it looked at the old Buck at the Ross campus. This is the table. This is the hoist. It's kind of cool how these different systems get into the lead shield, which I'll talk about in a second. And then the other detector that we have is from Lawrence Livermore National Lab. It's actually 2 detectors and 1 shield. It's that picture that you can see there. And those are called Rhyme and Reason. Okay, go ahead and go to the next one. Okay, so what are these counting stations? So I told you they're really good radiation detectors, but I haven't necessarily told you what they look like. What you can see in this picture is the black part. That's the germanium crystal, and that crystal is actually what is detecting the radiation. You can see a sample, so I can't tell what that is. That's maybe some screws or something that we have put in there. So we put our sample on the crystal, and then around it, we have a copper box, and then we have a huge stack of lead. And the lead is to make sure, just like we had with this demo, is to make sure if I have some source out here, like the cavern walls, for example, and I have my radiation detector, and I want to do a low background, a really ultra pure material, I would want to have this lead here so that I would only count the gammas coming from my sample and not from this bigger source outside. So that's why we have the lead shields. Okay, go ahead and go to the next slide. Okay, so now we're going to the tour portion of our afternoon. And I'll go ahead and open up one of these Berkeley detectors. So this is the Maeve detector that I'm going to go ahead and open up. So when you're looking at a detector like this, what you're mainly looking at is a huge lead castle. And so you always have to open the lead somehow. And so all 3 different groups have different mechanisms of opening the lead castle. This is the Berkeley way. So I just pull this up here. You can see there's lead here, so that the lead will be over the crystal too. Just give me 1 second to put the handle on. Oh, I'm nervous. I'm going slower than normal. Here we go. Okay, so inside, you can see the copper housing. You can see the crystal here, the copper, and the lead. So if I were to change a sample, I would prepare the sample. Of course, we have to prepare the sample carefully too, because these samples are ultra low radiation. So you have to wear gloves. You have to make sure you're cleaning everything carefully. You have to be careful what materials you're using to hold your sample, because those also have to be low background. But that is what one of these things looks like inside. Each shield has about 500 lead bricks. And so I think we've got about 2,500 lead bricks in the Buck. And I think each lead brick is 26 pounds, and I can't remember right now, but I remember thinking that we have about 60,000 pounds of lead in this room. And that's just around all these detectors. So big thank you to all my students and all the surf people who helped us move this. Okay, I'm just gonna close Maeve back up. And you can see down here, if you wanna look, Matt, the crystal is actually entering the lead stack through the bottom of the stack. Sorry, there we go. So another kind of interesting thing about these stacks, I'm going to go back over here really quick. Is you have to, oh, okay. You have to stack the lead carefully, which is kind of funny because you would think, okay, maybe you could stack one of these in a day, but some thought actually has to be put into how you stack the lead. And I brought some blocks in. I have a 3-year-old daughter and she loves these blocks. But I brought some blocks in just to kind of demonstrate how we stack things. And really the goal is, say my crystal is here. The goal is to make sure there's no line of sight. So you see this crease here. So you could think that a gamma could get in here and hit the crystal. And so that's not great. So we're gonna put maybe a brick here. And then we get rid of that line of sight. And then we keep going. But we also don't want any vertical problems either. And so instead of stacking these on top of each other, we might stack them something like this. And so this turns into a giant game of Tetris, especially on some of our detectors. One of our detector, Morgan, we had some lead that had been underground for a while. And lead that's been underground for a while has lower amounts of radiation coming from it. And so we wanted to put that close to the detector. But the problem with those bricks is they weren't a standard size. And so my student, Ayla, who I'm tried really hard to be here, but I think the snow kept her bound. Hi, Ayla. She was going to talk about her design because it really took her quite a lot of time to make sure to mesh those old lead bricks with the new standard ones. And she did a great job with Morgan that's stacked over there. Another thing that you might notice about these detectors is they're covered in mylar. And this is just a mylar aluminum sheeting. And so another fun thing, another thank you that I should say today is to Robin Varland, who helped us wrap Morgan today. So it's kind of like wrapping a present. It's kind of fun. So we basically want to wrap the entire lead stack. And perhaps, Matt, I'm sorry. Well, I'll talk about this first. You have to wrap the lead stack with this mylar. And the reason that we do that is because we have the lead break shielding, keeping any stray gammas from the walls or our bodies or anything like that from getting into the crystal. But then also we have to think about the air. The air is actually radioactive. And in particular, I think South Dakotans know this because when we bought a house a few years ago, we had to get the basement tested for radon. And the same thing underground. We have radon levels underground, and radon is radioactive. And so just like if your basement tested too high, you have to get a radon mitigation system installed in your basement. This is our radon mitigation system. And to really understand why that is, what we're doing is we're flowing gas into the bottom of these and then hoping that it trickles out. And so the mylar is basically just to keep any radon out and to keep flushing the volume with the cleaner nitrogen. And that cleaner nitrogen, we actually use liquid nitrogen to get clean nitrogen gas, which is kind of something that you might not know about if you weren't in physics. It turns out that the boil off from nitrogen, liquid nitrogen, so this is a doer of liquid nitrogen, it turns out the boil off is purer than a lot of the bottled nitrogen that you can buy. So what we're actually doing with this liquid nitrogen doer, I'm not using liquid nitrogen out of this doer right now. I've got it hooked up to the wall, and you can see this piping going around the entire room, and it's going on that side too. And what that's doing is that's going to flow meters and valves, and that's being pushed into these different, basically what we've made are 2 mylar bags here. And so we're hoping to push the clean nitrogen air in and the radon out. Let's see. So I showed you the opening mechanism for the Berkeley detectors. I think we can take a look at the Livermore detector, Rhyme and Reason. One of these has been sent back for repairs, so you can only see one. Eventually, we'll have 2 detectors in here, and I think you could see in the slides that we saw earlier, the 2 detectors were like this. But this shield is kind of cool because it just shuts that way, and then to open it, we just pull it out. And you can see it still has common features, right? So it's got the copper. These are filled with lead, and this is filled with lead. So that's another opening mechanism. And then the final opening mechanism we can't see yet because it's not in, but you can see the hoist here. And so germanium 4 is actually a detector that will sit under the table and it will go up. So all of these are going into the shields. This one will go up into the shield. So its shield will actually sit right here. And what they've done is kind of similar to this, where you have a door that's filled with lead. And their doors will be, let's see, I forget. Their doors will be over here, I think. And they'll use their hoist to grab a door, lift it, and put it out of the way. And then that's how they'll change their samples. So there's just kind of 3 different points of view on how to change samples. They all have their pros and cons. One other thing that I thought, one of the cool, oops, we almost lost Matt. One of the cool things about seeing us in progress is these detectors are pretty much finished now. But the one that we plan to work on starting in a couple weeks is the twins. And the reason that we call it the twins is because it's got 2 crystals. And these actually aren't where they will sit. But this one will come into the shield here. And this one will actually be sitting here and pointed this way. And so when they're done, they'll both be pointed in like that. But you can kind of see how much lead it takes to move one of these detectors. It takes a lot of lead. So we move the lead in, and then we stack it here. You can see there's 4 layers already stacked for the twins, and we've got the copper. The next step would be to reposition the dewar, so over here, stack the copper, and then this detector has a carriage that's much bigger. So this is actually the carriage that will sit on top of here, and then this will be the copper box that goes over it. So it's kind of fun to see it in work. This is what the crystals look like. So all of these Berkeley detectors all have what's called a cold finger that comes out of the dewar and enters the shield. Another thing that you might be wondering about is why we're wearing gloves and booties and things like that. Right now is kind of a weird time in the buck. So the buck will normally be a clean room. So right now it's kind of a pseudo clean room. It's a clean room. What really makes a clean room is the air handling. So what clean rooms do is they push clean air in and then they push air out, and they do it fast. So it's all about air turnaround, because once you have something dirty, you want it to go out and you want to replace it with the clean air. And so this is a clean room in the sense that its air handling is working, but it's not necessarily a clean room right now in the sense that we're not gowned up, for example. So normally I would gown up to come into the buck, but we aren't right now because we're moving lead. So you guys happen to catch us on a good day. So since we're moving lead, that's intrinsically dirty. And so today is what we call a dirty day. And so we move lead all day today. And tomorrow the space will be cleaned. It's kind of cool, the cleaning procedure that they do. They start with the ceiling and go down. So they do the ceiling, they do halfway down, they do down, and they go from the back of the room to the front of the room. So you got to get all the dirt down and out. The other thing, I don't know if Matt's going to be able to see this or not. We didn't talk about showing you this. So to tell us what kind of a clean room we have particle counters. And so what determines how good of a clean room you have is how many particles you have per a certain volume of air. And so what we tend to use is particles that are 0.5 microns. So that's 0.5 times 10 to the minus 6 meter particles. And so actually, we're doing pretty good right now. We're in a, so that's how many 0.5 micron particles are in a cubic foot? And right now, the particle counter is telling us that we have 100 particles per cubic foot. So we have a class 100 clean room, and I'm not even garbed up. So that's pretty good, actually. This room has really good high turnaround, air turnaround. So normally, if I was in here, I'd be garbed up, and you would only be able to see my eyes. But today's a special day. Well, I think that is all I had, and I would be very happy to answer questions.
A lot of questions.
Okay.
Is this an okay spot for you to take them, or do you want to? Okay. Can you hear me okay, Brianna?
So, Aaron, you were talking about one of those technical problems, and right now we won't be able to hear you at the question. So I can see the questions, and I will go ahead and ask Brianna the questions if that's okay.
Should we go to your laptop?
Yeah, let's walk over to the laptop, and we'll both be able to see. All right. Can you see those?
Yeah. So I've got one question that says, where do the germanium crystals come from? That's a really good question. So they come from different places. So there's two main manufacturers of what we call high purity germanium crystals. One's called, they've changed their names, but they were used to called Ortec and Canberra. I think now they're Amatec and Mirian. And depending on where you get your crystal from and what sensitivity you need, crystals can be grown underground. And so right now we're buying crystals from these two manufacturers, but there's also groups working on growing crystals underground. And we've also collaborated with the University of South Dakota on their crystal growth too.
Good. Let's just go through the list.
Okay, I'll just keep going. What would it do if you put that Fiesta plate in there, meaning the counting system, I think? So normally, I might have mentioned, I can't remember, we usually count samples for 2 weeks, and that's because we have ultra low radiation samples. I think if I were to put that Fiestaware, we could count for maybe 2 hours, and we would see a huge spectrum even from that 2 hours, whereas a huge spectrum would take us 2 weeks to gather from a low radiation sample. So I think that's the answer to that one. It wouldn't take long to count, that's for sure. I've got a question. How often do you have to fill the detectors with liquid nitrogen? So that's a really good question. We actually have a couple different systems in the room right now. So you can see here that we have a liquid nitrogen dewar. And at the old Buck, we had to fill the dewars every few days. But in the Davis, one of the things that we had to do was we had to upgrade our detectors to dewars that actually recycle the liquid nitrogen. And so this dewar will actually keep this amount of liquid nitrogen cold for 2 years, which I think is pretty nice. And actually, Doug Teep designed a system so that we can monitor these from anywhere. So you can see this one has a liquid nitrogen level of 92%. It's telling us it's okay, and it's using about 50% of its power to keep this cold. And this is the pressure that it's at right now. So yeah, so these are a lot nicer. I have had to fill these with liquid nitrogen, so I did have to use that dewar for liquid nitrogen, but I don't plan to for another year or two. So that's kind of a nice perk of the new detectors. Now, this detector actually, so there will eventually be one detector here, but this detector that's here doesn't need liquid nitrogen. So this one's electrically cooled. So that's nice too. Okay, let me see what these questions are. How much does one of those lead bricks weigh? So these weigh 26 pounds each. And so I'm not going to be able, I'm on the spot and I'm not going to be able to do the math, but each one of these castles would have like 500 times 26 pounds of lead in the lead brick castle. Do you have to worry about exposure to lead and lead poisoning? So yes, so safety is something that, of course, Sanford Lab takes very seriously. And there's a whole course that you take before you're allowed to even touch one of these lead bricks. These lead bricks are actually very clean. They've done a lot of monitoring. When we've moved the lead bricks around, we used to wear N95 masks and that sort of thing. But they did dust monitoring, and the levels came back very low. And so we do have to worry about it. We're very careful to wash our hands. I'm wearing gloves. If I were to move that, I would be wearing leather gloves. The other thing that we have to do is wear metatarsal guards that kind of look like night boots. I don't know if I should get some out. They're kind of fun. It feels like to me that they look like something a knight would wear. And so we put these on our feet to guard our feet, and we're just very careful. We take lots of breaks. We make sure to wash our hands, but there's not much lead dust in the air that we have to worry about from these clean bricks. Okay. Is all of the copper in the various modules the ultra pure copper that you grow? No, so it's not. I actually think that for germanium 4, they're talking about it. But for these counters, we didn't use the copper that we grow is actually grown right there in the electroforming room. But no, the copper that we use here is called oxygen-free high conductivity copper. So it's basically as pure as you can buy, but it's not the electroformed. How big and what kind of samples do you get? So it depends on the sample. For the past several years, we've been really concentrated on LZ samples for the LZ detector. And so those kind of ranged all over the place. We did their PMTs, their light detectors, which are maybe this big. We did some other samples of liquid that would be, I should have brought one down, that it would be in a Marinelli beaker. So they actually make beakers that will fit onto the crystals, and those are called Marinelli beakers. So you can basically fill whatever you can fill that up with. So the samples are usually like this because they have to be able to fit in the detector, and we have to shut the lid. You're always trying to get the samples as close as you can to the end cap of the detector, but really could be anything. It could be a plastics, it could be, I feel like we've done a million screws, could be anything. Okay, this is a bit, oh, it just disappeared. So the question was, do you know that Maeve was the goddess of drunkenness? And I did not know that. What I'll tell you, that's a little bit of the history with Al Smith, actually, with the Berkeley detectors. You'll notice that Maeve, Morgan, and Mordred, for those of you that like legends, are actually from the Arthurian legends. And Merlin is a detector that's at Berkeley right now. So I think Merlin started out, and then I've heard it, Queen Mav was from the Arthurian legends. Morgana was, I think, Arthur's sister, and then Mordred was their kid. So I guess this was kind of the bad one, because I think he ended up killing Arthur. So yeah, so there's kind of a fun play with the Arthurian legends. How much does a typical germanium crystal cost? That's a good question. So each one of these systems with the lead and everything probably costs $250,000 each. So that's the cost of the crystals. Let's see, sorry. Is the Mylar on these detectors the same as a Mylar balloon? I'm actually not sure. I don't know. The reason that we chose Mylar was because it's good at keeping radon out. And so that's why we chose Mylar. I don't know if I could have like gone to the dollar store and got a bunch of Mylar balloons and done the same thing or not. I'll have to look at that. It'd be maybe more fun to have them colorful, like the pink balloons. Can you go into the history of the lead bricks? I have heard that some of them may be historic. So a lot of the lead bricks that are in this lab come from a particular mine called the Doe Run mine. And so that's a mine that's known for low radioactivity lead. I mentioned that Solo had some old lead in it. And I actually don't know the history. What they call it is the old German lead. And I think it was I'm going to get this wrong, but I think it was lead that was in a basement in Germany since the turn of the century, the last century, the 1800s to the 1900s. So it had been underground for a while, so it's low radiation lead. But we don't have, I have a feeling that this person probably thinks that we might have some of what they call ancient lead that the Italians have. So back in Roman times, there were shipwrecks that had lead in them. So they've been under, I don't know, the Mediterranean for 2,000 years. And they, archaeologists work on these wrecks and they found this lead. And I'm not sure how the physicists got involved, but they basically got some of this lead. And so some of that ancient lead that's 2,000 years underground is in Italy. Let's see. What are the purest materials you have counted so far? I don't know what the purest has been. Some of the purest has been the LZ titanium, maybe, for their cryostat, for their detector. That may have been some of the purest that we've done so far. Do you have to clean the lead bricks? So it depends on whose lead bricks you're talking about. So the Berkeley lead, we don't need to clean. With germanium 4, they do wipe each brick with an alcohol wipe, with an isopropyl alcohol wipe. But no, we don't wipe our bricks. We are careful to keep them clean. So they are sitting out on the floor, but they're also sitting out on the floor in what we saw was a class 100 clean room. So no, we're very careful. And when we ship them, we make sure in the crates that we put plastic down and plastic over them to keep them clean. What types of PPE do you need to handle liquid nitrogen? How about low oxygen hazards? Okay, so kind of two different questions in one. So I can demonstrate. So this was good timing because we just hung these today. So when you use liquid nitrogen, you use a face shield, and then we also have special cryogenic gloves. And so whenever we're dealing anything with liquid nitrogen, we do that. Make sure you wear long sleeves, that sort of thing, because liquid nitrogen is so cold, it will burn you. One of the reasons that we had to redo the dewars for this campus was oxygen hazards. So kind of a funny thing with liquid nitrogen, if this were to rupture, it would displace the nitrogen in here that became gas, would displace the oxygen in the room, because this expands like, I'm on the spot again, 1 to 700 or something like that. And so it would expand, it would completely push out all the oxygen. And so we couldn't breathe. And so that's what they're talking about with low oxygen hazard. And so we do a couple things with that. We have an oxygen sensor here, down here, that is right next to the doer. So we will know if we have that hazard or not. Because one of the scary things with that hazard is you won't understand what's happening because you're still taking breaths, but you're not getting any oxygen. So you'll suffocate without knowing it. So that will tell us all of the guides that are underground wear gas testers that also have oxygen testing on them. And engineers have, thank you, Charles, have done, I'm forgetting what they're called, oxygen deficiency hazard analysis, ODH analysis on this space. So it turns out that, remember I said that the airflow was really good in here? It turns out that even if this whole thing ruptured, we'd be completely fine because of how fast the air is flowing. So there's very, very small hazard associated with that. But that is something that we think about underground. And, oh, I never finished my thought. The reason that we don't want to fill these is at the old Buck, we had 4 of these dewars that we would use to fill each one of these every few days or so. But that would increase our oxygen deficiency hazard here in the Davis. And so we were able to upgrade to the recyclers, and now we only have 1 dewar in the Buck at a time. Oh no, can't see the questions anymore. I moved away. Okay. I have no idea what time it is. 7 minutes. Okay, how do I, oops, I think I just got on something wrong. Sorry, how do I scroll? It's up and down. Sorry. One question says, growing germanium crystals underground implies that there is inherent radiation in crystals grown above ground. Is that the case? Yes. So, so I'm not, to be honest, I'm not an expert on the germanium growing, but I think when you're on the surface, you have particles bombarding us all the time. And what some of those could do is activate isotopes of, say, germanium that are radioactive. So maybe germanium 76 is not radioactive, but a different isotope is. And when it's underground, you never activate, it's called cosmogenic activation. You never activate that other isotope that is radioactive. So, so yes, it is beneficial to go germanium underground. And underground doesn't necessarily mean a mile underground. So it could be in just 100 feet or so, and even beneficial.
Maybe do 1 or 2 more, and then you have a couple more slides.
Oh yes, I forgot about this. Yes, yes, yes. Okay, one or 2 more. What do you do with used crystals? I would love to have a used crystal. So we use these crystals for years and years and years. So we don't really have any crystals that we're not using. And so I think, I'm gonna get this wrong. I think Morgan and Maeve might have been operating for decades. And the twins as well. The twins were actually some crystals that Kevin Lesko found at Berkeley, and we reworked them into being low background. And so who knows how old those were. So we reuse crystals. We just don't have crystals lying around. I would love to have crystals lying around. In a typical experiment, how many samples do you have to assay? So that's a good question. I don't think people realize how many assays we do. So we've been operating 4 detectors since 2015, I think, so about 5 years. And we were fully booked the entire time with just LZ samples. So it took us about 5 years to just count LZ samples. And I'm gonna get this wrong, but I think we did thousands. I think the final count was like 2,000. I should have looked that up. But so one of these projects takes a lot of time just for the low background counting. Is it unusual for students to have an opportunity to work in a facility like the underground campus? I love this question. So no, it's not. So with BH students, I wish Ayla could have been here. My student Ayla has been completely instrumental in helping me move the buck. So were Sierra Ward and Danica Koser from BH. Danica and Sierra are both athletes, so they couldn't be here either. So I'm kind of flying solo tonight, but this is definitely not a solo thing. And I usually have 1 or 2 students working with me each semester. And then we have 2 to 4 students working in the summer. And so if any student approaches me, I'm more than happy to work with them usually to come underground and get involved with the buck or even some of the other experiments that are going on here. And that's actually a really good transition to my last slides. So maybe Aaron, could you bring up the last slides? opportunities for students. So go ahead and go to the next slide. So a few things here, and since this is International Women in Science Day, I just wanted to put a plug in here for QWIP. So QWIP is the Conference for Undergraduate Women in Physics. We just had one a couple weeks ago. They happen every January. Usually they happen around the country in 10 to 12 different sites. This year was a weird year, and so we just had one virtual one. Usually there's 2,000 undergraduate women in physics that attend these things. We had one at Black Hills State last year, 2020. We squeaked it in before the COVID stuff happened. But they're a great opportunity. So if you're an undergraduate female student out there, you should definitely look into going to QWIP. I put the 2021 locations in there. We just announced those, so we're really excited about those. Go to the next slide. If there are other undergraduate students who are interested in doing research at SURF, I am currently taking applications for our RU program. So RU programs are funded by the NSF. They're 10-week summer programs, paid summer programs. They pay you a stipend, they pay you room and board, they pay you travel to the site, and you can work underground. And it's not just limited to physicists, our site. So our site, the BHSU SURF site, has physics students, chemistry students, and biology students. In addition to getting research experience, you also do professional development activities, listen to different faculty, give research talks, and then we have lots of social stuff. So the Black Hill's kind of fun, so we go on hikes and that sort of thing. So if you are an undergraduate who is interested in research, definitely put in an application. Those applications are due at the end of February, so you only got a couple weeks. Okay, go ahead, next slide. Okay, so if you're a middle school student watching this, we have a BHSU underground robotics competition. It's kind of on hiatus this year, but hopefully we'll be back in the fall. We have teams of middle school students. So two middle school students work on one robot, and then they also work with a college mentor to design their robot to compete underground. So you have to be 18 or older to be underground, and so that's why a college student teams up with the middle school students. So the middle school students have a great day after they design their robot. They come to surf, have pizza, and watch their robot compete underground with the college mentor. So that's kind of a fun project as well. Next slide. Oh, and then a side effect of this is that we've had lots of teachers underground. So this is Andy Johnson and Leslie Wongeman, both middle school teachers. I think middle school, since we're talking about the International Women in Science Day, for physics, I think it's been shown that middle school is kind of where one of our leaks in our pipeline is. And so if you ask girls versus boys how confident they are in their ability to do math and science, they're about the same. And then girls their confidence drops off in middle school. And so I think we always like to work with middle school teachers, especially, and the middle school students with the robotics competition to maybe do our little part to maybe help that leaky pipeline a little bit. So I think that's all I have.
All right, we'll kick it back over to you, Erin.
Well, I don't know if they can hear me over there, but I certainly hope you guys can hear me. I just want to give a big thank you to Dr. Brianna Mount for being our speaker tonight. She can't hear me and she probably can't see this, but we have an awesome photo for her. It's mounted on bamboo, and it is the Ross head frame over Kurt Canyon. And fittingly, it is covered in snow, which we're getting a lot of today. So we also have a surf pin for her. So we want to thank her for doing this talk tonight, staying underground late after a full day working underground. We also want to thank our Deep Talk sponsors again and the entire communications team, especially Matthew Kappas, for making this possible. And I'll end with a quick reminder that our next Deep Talks is Thursday, March 11th with Dr. Travis Kowalski. He is an award-winning mathematician and a mathematics professor at South Dakota School of Mines and Technology. A recording of this talk will be shared on Facebook, Vimeo, and YouTube channels, so feel free to share that with a friend who missed the live event. When you leave, you'll be given the option to take a survey about Deep Talks. We'd love to hear what you have to say, so please do leave us some feedback. Thank you for joining us tonight. Have a good night.